Hello, this is Timothy Wood with Citadel Civil Engineering. This is CIVL202 Statics, and in this lecture, we'll be discussing vector mathematics. So we're just introducing the idea and laying the groundwork for vector mathematics. We'll be doing a lot more with it for sure, but we want to start by defining some terms and laying out some content. We're in chapter 2.2 and 2.3 of your textbook if you want to follow along. And the first place we want to start is by talking about scalar multiplication and division. And so the idea here is that we might have a given vector. Let's say that we have vector C, and we'll remember that vectors have magnitude and direction. They start at their tail, they go to a head where the arrow is. And when we think about this particular vector, if we were to multiply it by a scalar value or divide it, that'd be the same idea, just multiplying by 1 over, we might have the vector here. We have vector C, which we'd indicate this way. If we wanted to have 2C, we would note that it would have the same direction. So this is what makes scalar multiplication easy. And what we would do is we'd simply double the length because we're multiplying it by 2. Or if we wanted to do 0.5C, we'd cut it in half. And so when we do scalar, we're multiplying the scalar component, the magnitude, by a constant that's either increasing or decreasing its length, and we're not changing the direction. Now, the only exception to that would be, of course, if we multiplied it by a negative value. So if we have negative C, all that negative does is basically flip the arrow around. So it's along the same line of action, but now in the opposite direction. So it's a negative C, like so. So that's scalar multiplication. There's a great figure in your textbook that actually goes through this exact thing. Pretty clean, pretty straightforward. Now, the next concept we want to talk about is one called a resultant of a system of vectors. And so this is going to be the vector summation and summation is just a fancy word for addition, of a set of vectors. And the way we would express this mathematically is we might have something like V with an arrow over the top to indicate our vector sub R, and we'd use that capital R for the vector resultant, is going to be equal to an uppercase sigma, that's meaning summation, of some collection of vectors I. And we'll notice it has the arrow over the top. And so the way we'd read this is the resultant vector is equal to the sum of the vectors. And we can't just add up the magnitude, because when we do vector addition, when we do summation, we are going to have to think through both the magnitude and the direction. And so with that in mind, let's start talking about our vector addition. So the challenge we have in mind is that we might have a system of vectors, vector A and vector B, like so. And we want to be able to add these two to come up with the resultant vector. So our fundamental question is we want to be able to solve for a resultant that's the summation of vectors A and B. And the first way we might do this, which is covered in your textbook, is using what's called the parallelogram law. Parallelogram, I'm going to move these down a little bit. Parallelogram law. If you remember back to your geometry, this would be a proof that we could do. We're not going to do that proof, no need to panic. But in that proof, what we would do is we'd start by taking our two vectors and repositioning them so that their tails overlap, like so. And you'll notice I didn't change the magnitude, they're still the same length, and I didn't change their direction. And in fact, we might introduce some sort of reference line here. And then we'd have an angle here, theta B, and an angle here, theta A, to indicate their direction. And from these 2 points, we're now going to draw a parallelogram. So if we remember our geometry, by drawing a parallelogram, I'm going to start at the head of B, and I'm going to draw a line parallel to A. Kind of be tricky to do on a whiteboard. If you've got a straight edge as you're taking notes, I highly encourage you to do that. And then I'm going to go to the head of A, and I'm going to draw a parallel line parallel to B, like so. How's that looking? Do y'all see a parallelogram? It looks like I got this a little bit more, a little less angled than it needed to be. Something like that. All right. So now we have a parallelogram drawn. Good? It's looking good? All right. And if we want to know what the resultant of this is, we start at the tails and we draw a diagonal to the other end of the parallelogram. And that's going to be our resultant. Now, you might ask yourself, Dr. Wood, you've just drawn a pretty picture. How does this help us? And the answer would be that a vector quantity we're going to use all the time in statics is the idea of a force. A force is just, remember, the push or pull. And when we think of a push or pull, it's going to have a magnitude. How big is it? How hard are we pushing or pulling? And a direction. What direction are we pushing or pulling? A classic example of this is if you ever walked more than one dog, each dog is going to pull on their leash, and you're going to have a force vector pointed along their leash. It has a direction, and then a magnitude based on how big the dog is. And what we would want to find is the resultant force that's the sum of all the forces. Well, if you take all those dogs and all their pulling together, you'd get that resultant force. Just how hard are they pulling, U total, and in what direction? And that's what this resultant would give us. So we could draw a parallelogram. And if we wanted to solve for the angles, we'd have a couple of different ways we could do this. We could solve for the magnitude by just drawing it to scale and using a meter stick or a ruler to go ahead and measure that length. If we wanted to know the angle, we could use a protractor and go to our reference line and find out what that little angle is. And that would be a totally fine way to do it. But I am pretty certain y'all aren't particularly excited about drawing these vectors out. And so instead, what we could do is we could use instead the triangle rule. The triangle rule. And so when we use the triangle rule, what we're going to do is we're going to, instead of drawing do y'all see some triangles up here on our parallelogram from the parallelogram law? Well, I see a triangle. What happens if I move vector B to here? Well, you see, I didn't change the direction of B. It maintains the same direction, the same magnitude. And by going from head to tail, working their way along with the triangle rule, all I have to do is then connect the last tail to the first head, like so. And I get that same reference line. And then again, I can do this to scale. If I have, this also helps us see that the vector addition is commutative, meaning that A plus B is going to be equal to the same as B plus A. So it doesn't matter what order I do, I'm going to get the same resultant force. So that's going to be very important to us. Sometimes this is called a force polygon because it turns out if you wanted to add multiple vectors together, you could just do head to tail, head to tail, head to tail, and then close the force polygon with that last vector. So I could, if I wanted to do A plus B plus C, I would head to tail, and then that would be my final resultant vector. And I can measure its magnitude and direction. Now that all sounds fine and good, but what if I want a little bit more precision? Maybe I don't want to just draw everything to scale all the time. Although in many applications, that's totally appropriate. For example, in geotechnical engineering and slope stability, using force polygons is a fairly accepted way to do this, drawing everything to scale. Because our precision in geotechnical engineering is so low. We know so little about the soil that a graphical solution usually gets us everything we might need. That said, if we wanted, I'm going to put it back, but if we wanted a more precise calculation, not necessarily more accurate, but more precise, more significant figures, we could use analytical trig to solve for this triangle. So we could use our sine, cosine, tangent, and then our law of sines and law of cosines, all of which are in your FE reference handbook. And so instead of doing that in this video, we'll do that together in class, and we'll explore how we can use the law of sines and the law of cosines to solve for this resultant force using everything we know about triangles. So we've got three methods that we can use. We can use our parallelogram law, where we draw a parallelogram, our triangle rule, where we draw a triangle. Both of those would be graphical solutions. Or I can turn my triangle rule into an analytical solution by using my law of sines and law of cosines. Now, naturally, if I wanted to do subtraction, all that's going to do, remember, a negative value flips the vector around. And so over here, I just turn my vector around and again, head to tail, but now I've changed the direction by inverting it. And so that would let me do subtraction. Finally, what if we had collinear addition? Collinear addition. Well, let's think about what that would look like if we did our head to tail rule. So if I have vector A and it shares the same direction as vector B, I can add them up head to tail like so. And so if it's collinear, the angle theta A is going to be equal to the angle theta B, which is also equal to the resultant. So the resultant goes from the initial tail all the way to the final head. That's our force polygon, except in this case, it's not a polygon, it's just a line. And that would give us our resultant force, theta R. And the magnitude of that resultant is simply going to be the magnitude of the two collinear vectors. So again, now there's no vector hat, so we're just going to add A to B to get our collinear addition. And so we can just sum up the magnitudes. And this becomes super helpful because it turns out we're not actually going to want to use the parallelogram rule law or the triangle rule or a force polygon most of the time to do our analysis. Instead, we're going to want to work our way to a collinear system and use straight up sine, cosine, and tangent and a Cartesian coordinate system to manage our vector addition. So we'll talk about that in our next lecture. I look forward to seeing you then.